Hi, everybody. Let me turn that off here. Just a few updates on the upcoming schedule. So hopefully everybody has read the announcement that I posted last night. I might need a little more time to go over all the material before the final. So I'm going to use part of tomorrow's lab lecture and QA as also more lecture content. I'm actually not super worried about this class because we're pretty much on track to finish. That said, I would like to use the time just to make sure that I can get all the stuff in time. The exam will cover all the content that we cover this week and all the way back to whatever we covered before or after exam number 1. There will also be a Chapter 9 quiz, which will be posted when we're finished with Chapter 9. There will not be a Chapter 10 quiz. I will simply just roll that content into the exams or final, whatever we end up covering. With that said, there is also going to be a lab tomorrow. I will unlock that later tonight so that you can look at that, and then it will be available. And yeah, it should be just like any other lab lecture other than the extra regular lecturing coming after that. So let's continue with Chapter 9. We are almost done with Chapter 9. We'll probably finish it today and start Chapter 10. So yeah. Let's talk about collision theory. Collision theory is basically the idea that all molecules are moving, and when molecules are moving, they bonk into each other. And if they bonk into each other with enough energy, they will react. But if they don't bonk into each other with enough energy, they don't. So not all collisions in a container with molecules, whether they're in the liquid phase, gas phase, or whatever, are going to result in reactions. An analogy for this would be if you threw a ball at the wall, the ball would bounce off of it and it'd make a loud sound. It'd just thunk. But you could probably imagine a situation where you throw the ball hard enough, and when I say you, I mean like with like a cannon or something, and you launch it at the wall, and it could go through the wall. It could cause enough damage that it would break the wall. That would be the difference between a reaction, as in the wall breaks, and no reaction, where the ball just bounces off the wall. The amount of energy that you need to do that is some threshold, and that energy could be calculated. In reactions, we have done that. And so we will represent that using a picture to show you what we mean. So there's 2 criteria that we care about. We're not really going to care so much about orientation in reactions because this is an introductory class and that's a more of an advanced theory. But the most important thing to take away is that we need a minimum amount of energy to cause a reaction when 2 entities collide with each other. This is called the activation energy. The activation energy is the amount of energy you need for the reaction to happen. And pictorially, we're going to draw that as like a hill. So like I'll have something at the bottom of the hill, and then if I can throw the object high enough to get it over the hill, it had enough energy. But if I didn't throw it high enough, it will hit the side of the hill and come rolling back down towards me. Now, when we do chemistry, or any sort of reaction outside of the laboratory, you will probably see that energy is involved in some way. For instance, if you have a wood-burning stove or fireplace or something like that, I guess you wouldn't have a wood-burning stove. Who uses that anymore? If you have a fireplace, though, and you put wood in it and you light the wood on fire, you don't do that because it's pretty. Like, there's a very specific function for burning firewood in your fireplace, and that's because it releases heat. So what you could say is that if we were to compare the firewood versus the ash and stuff that's left over, and all the combustion products too, which would be CO2 and H2O, we could say that the firewood itself has high energy. Now, that would be potential energy. The reason it's not kinetic energy is because it's not moving. Potential energy is energy that's stored in bonds, like we talked about in Chapter 7. We can turn that potential energy into kinetic energy by making gaseous products like this. The water that you make when you burn stuff is a vapor. So this would be considered to have low energy, because we've converted it all into another form. If I were to draw a diagram of this, this is kind of what it would look like. So on the y-axis, we're going to have energy. And on the x-axis, we're going to have reaction progress. And what this just means is that how far through the reaction are we before anything has happened, or are we after the reaction has occurred? So in other words, on the left side, we're going to have reactants. And on the right side, we're going to have products. And we're going to plot their energy coordinate based on what we said over here. So we could say firewood has high energy, so I'm going to put it high up here. That's actually a really bad line. Let me try to do that again. And we'll just put that on there. Firewood. And then what we could say is we could say that, well, the other stuff that we made, so ash, CO2, etc., is low energy. I did that in the wrong color. That's okay, though. Now, in order to get from reactants to products, I would have to draw a curve to connect the two. But if I do this, then what's implied by this reaction is that firewood would spontaneously just turn into ash and carbon dioxide and all the other things on its own. As far as I am aware, firewood does not spontaneously self-combust. And so this diagram as drawn would not be right. So we can't do this. What we have to do is we have to put activation energy in there. So we'd have to do something like this. In other words, I have to give the firewood some initial energy. And that's this right here. Now, when you light your firewood, you do so by using a match or a fire starter, like those little clicky things. When you do that, you are providing the firewood with an initial amount of energy to get the reaction started. Once you've provided that energy, the reaction goes on its own, because the energy that is produced by the reaction is, once it's lit, it would be this much, right? Well, we've already paid this much energy to get the reaction started in activation energy. So this difference right here would be the energy of reaction. The energy of the reaction is the difference between the reactants and the products. Now, because the energy was lost from the reaction, because the total energy went down, the energy must have gone out of the reaction, which is the firewood itself. So the energy is coming out of the firewood, and we perceive that as heat, which is why we do this process in the first place. We're cold. We want warmth. Let's set things on fire. You might see this term written for energy, delta H. This is a thermodynamics term called enthalpy. You could just think of delta H as energy that comes out of a reaction or goes into a reaction. We're going to talk about exothermic and endothermic in just a second. But that's the gist of what an energy diagram will look like. So when I put all this text on the screen, because I'm going to have to clear this in a second, it will say that. Here's a generic reaction. You can think of A and B as the firewood and AB as the ash or whatever, plus the heat that's released. So here is that again on our diagram. Since my reaction releases heat, the reactants must be higher in energy than the products. When something releases heat, you're going to perceive that as hot. That's going to be an opposite to if something absorbs heat. If you touch, like, say, an ice cube with your finger, the ice cube absorbs heat because it will start melting. And the feeling that you will perceive on that is, oh, cold, brr. And the reason for that is because your thermal energy is being transferred to the ice cube, which is what our body interprets as cold. These are just the same terms that we talked about before. So this right here is delta H, and this is the activation energy. I didn't mean to cross it out, I meant to underline it. There you go. All right. For this specific reaction as shown, the energy is leaving the reaction. For any system where this happens and the energy is lost from the reaction and gained by the surroundings, we use the term exothermic. Exo meaning out, and thermic meaning thermal energy. Delta H is not activation energy. Delta H is this difference right here. Activation energy is this difference right here. They are two different things. There is not a term for activation energy for this class. If you look in different textbooks, you'll just see this E sub A thing. But we'll never use that term. I will just say activation energy. But they are different things. Another thing to remember about the energy released by the reaction will be it's the difference between reactants and products. Whereas the activation energy is just the highest point on the graph relative to where you start. In order to get this reaction going, I got to get over this hill. If I don't give it enough energy, nothing happens. This would be kind of like if you light a match and then put it next to the wood for like 1 second. You didn't give it enough energy, so it didn't start. But if you hold it there for like 5 seconds, then you have given it enough energy and it will start. All right. So again, if a reaction releases energy, that is, the reactants have higher energy than the products, and the energy is emitted, we call it exothermic. Exothermic reactions feel hot. The opposite would be something that is an endothermic reaction, where the energy goes into the reaction. Now, what would a diagram look like if it was endothermic? Well, that's actually what I want you to try and draw. You've seen the exothermic example, so I want you to try this example. So, let's suppose you have something like a cold pack. Hopefully, people have seen cold packs or used them before. In the cold pack are some chemicals, and I'll just call them A and B, because we don't need to know what they are. When you break the seal, the chemicals mix, and then it gets really cold. And so you make a product, and the product, the result of the product being formed is cold. Sorry, I was trying to not spoil the answer here. So what I want you to do is draw an energy diagram for the scenario. The energy diagram, or the activation energy is not 0, but it is small. Tell me if the reaction is exothermic or endothermic, and then write a chemical reaction like we showed before. So I did AB, or A plus B makes AB in heat for the exothermic reaction. Try and write a reaction like that for the endothermic reaction, using the same process that we did before, which is, okay, where are the energies of the reactants relative to the products? Draw those first, and then draw a curve. And then identify all of the parts of that as shown here. Okay, so I'll give you a few minutes to do that. We'll go over the answers in just a second. I'm sitting here talking for like 10 seconds. I realize I didn't actually click the thing. Hopefully everybody has drawn their diagram. So what I'm going to do is go to here. And that's probably good enough for now. I got to zoom this in a bit so we have some space to draw on. And I'll do that. All right, so we know that the reaction involves us adding these two things together, and there's my text, okay. And we're going to make this. Now, we also know that the reaction is cold. So if the reaction is cold, that means that our heat needs to get absorbed. We can't release it. If we were going to release it, it'd be a product. So we're going to add it in as a reactant. We're going to remove heat from the surroundings and put it into the reaction to make the product. It's really hard to write sideways on this thing. I mean, I guess I could turn the tablet sideways, but then I don't know where I am on the screen. All right, so we got the reaction progress on the x-axis. We got energy on the y-axis. I know that my reactants must be lower in energy than the products because I have to add heat to them. So I'm going to put my reactants right here and my products over here. So this would be A plus B. And this would be AB. And the heat we're going to add would be this much. But I am also supposed to have some sort of activation energy. So if I do this, then nothing is stopping my reactants from just, or my products just going back into reactants. I need them to get stuck over there, so I got to get rid of this line. So we need some sort of activation energy, like this. And so now we need to describe the activation energy and the energy gained or released by the reaction. So first of all, if this line continues this way, that's not a very straight line, but it's okay. This would be the energy that the reaction gained. And because we are not the reaction, we are on the surroundings of the reaction, we feel that as energy being lost. It's cold. Sorry, that's my chair creaking. So this would be delta H. Remember that delta H is the difference between the products and the reactants. In red, the activation energy is this peak up here, and that is going to be relative to where we started. And so this I messed up. Hold on. Is our activation energy. Activation energy is always relative to the reactants. If I wanted to do it relative to the products, I'd have to reverse the reaction and draw the diagram that way. In fact, if I were to reverse the reaction, then the diagram that you would see would look like what we did on the previous slide, which let me see if I can actually squeeze that into the top corner. There we go, yeah. So you can see that the reaction for the exothermic diagram is just the opposite of what we did. That's the next slide. All right. And so we have already drawn the energy diagram for this, and we put heat in there, so we're all set. All right, so now you know the difference between an endothermic reaction and an exothermic reaction, as shown. And again, because this one gained reaction or gained energy, it's endothermic. So your job will be to look at a reaction, tell me if it's exothermic or endothermic based on where heat shows up in it, and then attribute it to the correct diagram. Other things you'll have to do is I might show you a diagram and you'll have to click on where like delta H is, or where the activation energy is, or whatever. Or you'll have to click on is it exothermic or endothermic, or something like that. All right. Here's the homework practice for this section. So that's energy. The next thing we're going to talk about is kinetics, which is how fast reactions go. And this is the fun section because I get to show you a lot of videos, including one that will probably get me a copyright strike. So we're looking forward to that. Because that one I'm not going to mute because it's just great. All right, here are two reactions. One of them is fast and one of them is slow. Which is which? I mean, duh, right? Rusting does not happen instantaneously. If it did, we would never use metal anything because it would just be immediately useless. Rust is a very slow reaction, whereas explosions are extremely fast. We use different reactions for different things. For example, if we want to impart a large amount of energy really quickly into something, like, say, a structure because we no longer need it, we would demolish it by setting up dynamite or some other type of explosive. If we want something to persist, we want the reactivity of that thing to be very slow. So we can make things out of steel because rusting is a very slow process, and we can either polish off the rust or replace the thing in question or whatever. Understanding how reactions go quickly and slowly is very important because that allows us to manipulate them and give us the flexibility we need for whatever task that we're looking at. In biology, we're going to look at catalysis and enzymes and things like that, and we want reactions to typically go fast enough so that life can be supported. If a reaction slows down, that could be toxic or deadly to a person. So this has biological importance too. So the speed at which a reaction goes is called its rate. The rate of the reaction is, in other words, just how many molecules react per second. Now, obviously, that's going to be a ginormous number, so we usually use like moles or moles per liter per second, things like that. But the study of this is called kinetics. Kinetics being speed. How fast does it go? In our studies in kinetics, we're going to narrow this down to 4 different things that can cause a reaction to go faster or slower. And those 4 things, I'm going to show you some videos to help illustrate the point. Now, we've already talked about why it's important. But here are the 4 things we're going to consider. So we're going to consider first we're going to consider the nature of the stuff that we're reacting. So like, is it a solid, is it a liquid, is it a gas, whatever. We're going to consider how much of it we have, which is concentration. We're going to look at how fast the molecules are moving, which is temperature. And then we're going to look at catalysis, which is a special sort of thing that allows us to change the energy diagram to something different, which can be beneficial. All right. I'm going to put this reaction on the screen, and I'm going to note that we haven't really used phases much, but in this specific reaction, the phases are going to be important. I'm going to react solid A with aqueous B. What that means is that my B is dissolved in the liquid, and A is just a chunky solid that I've dropped in there. So you can see on the screen here that the liquid is the blue stuff, and the solid is the pink thing. Now, depending on how I put it in there, I could either put it in as one solid chunk, or I could break it into several chunks. Which of these will react faster? And you might be looking at this and saying, well, does it matter? Well, kind of. Or you might immediately look at that and say, oh, it has to be B, because B has to touch A in order to react. All of the spaces where A is just trapped and surrounded by other A can't react. So that would be in the middle of this cube right here. So everything I'm highlighting, which isn't really showing up very well. This'll work. Everything in here that's in the center doesn't get reacted, but the stuff on the outside does. Whereas over here, and this is kind of hard for me to draw in because my thing is too big here. Everywhere that is on the edges reacts. And because there are more edges... Oops, I didn't erase all. Because there are more edges on this second one, there's more place for it to react. So reactivity cares about surface area because this is where the molecules actually physically encounter each other. If I have more surface area, the reaction goes faster. So I have a demonstration for this, so I gotta get this video up. And you don't need to hear the audio here for this guy, but I do need to pause it. So, window capture 2. What's this one? Boop. That didn't quite... Oops, that's the wrong thing that I want. Didn't quite get the whole thing. There we go. I don't need that part, and now I can make it bigger. All right, we'll leave the little demo question at the bottom here. I have 3 different containers that have HCl. So the HCl is the liquid part. And in each of these bowls is calcium carbonate. We're going to hit play here. And you'll get to see how chunky the... Oh, well, I guess you don't get to see how chunky they are. Let me go back a little bit here. We'll show you how chunky these are. So here's the first one. Which, yeah, good job, dude. We still couldn't see that. Okay, that's a little better. Alright. Here's the second one. You can see that the second one is a little chunkier than the first one. And then the third one is very chunky. So the first one over here on the left is very fine. This one's a little bit more coarse. And this one is just basically a few pieces. So I'm going to speed this up. Here we go. He's going to pour in the first one. Here's how fast the reaction is going. You can kind of visually see. I want you to tell me, is the second reaction faster or slower than the one on the right? All right, here we go. All right. What does that look like to you? Faster or slower? Go ahead and type it in the chat what you think. And I'll let it keep playing here. Oh, we don't want to see the next one yet. We'll just do this one again. So it looks faster. How can you tell? What observation is telling you that it looks like it's going faster? Oh, we have a different answer. What observation makes it look like it's going slower? Try and defend your answer. Type it in the chat. Tell me what you think is going on here. Yeah, very good. So it's making bubbles in the second one much more quickly than it is in the first one. Here's the third one, and the third one's very fine. Let's see if it makes even more bubbles. Yeah, there you go. So that seems to confirm that the reaction is creating a gas, which you couldn't really tell from the one on the far right. Let me pause in the middle when there's bubbles here. The one in the middle made a few bubbles, and the one on the right, or I'm sorry, the one on the far left made the most bubbles. And that's a direct correlation to how much solid was able to contact the HCl. When it's a fine powder, all of the molecules can pretty much react immediately. But when it's a very chunky solid, only the stuff on the surface reacts, and you have to keep digging down to the next layer to get to the next part of the reaction. So it goes slower. Alright, so that was the first factor that we can use. And so that was the physical nature. So grinding stuff up makes it go faster. Keeping it as a solid, a chunky solid, makes it go slower. Now, like we said earlier today, molecules have to contact each other in order to do a reaction. If you put more molecules in there, then the odds of the reaction occurring go up. So let's suppose that I had 2 solutions in a beaker. In solution 1, I have 1 mole of A and 1 mole of B. In solution 2, I have 1 mole of A and 4 moles of B. And A and B presumably react when they contact each other. Well, if I have a lot of A and the same amount of B, then the situation on the left happens here. Every A molecule will have a 50-50 chance of running into a B. The other 50% will be A. And A bumping into itself doesn't do anything. But if I have 4 moles of B, then I have a much greater chance of A reacting with B because there's just more B in the solution. So if I increase the molarity of something, I give more opportunities to react. Now, this isn't the entire story, because what about stuff like the solvent? So what does water do in here? Well, most of the solution is water. So most collisions are going to be with water, and bumping into water doesn't do anything. But if I can increase the amount of stuff that isn't water, then I increase the likelihood of the reaction. So if I increased A as well, I could then do this from the perspective of B, and the reaction would increase also. So if I have 1 mole of each versus 1 mole of A and 4 moles of B, that will go faster. But if I had 4 moles of each, it would go even faster still, because I am still making more collisions relative to the number of collisions with water. This one doesn't have a video. You just have to trust my graphic that I made. So, hooray. Maybe it has a video. Oh, it doesn't. Okay. Now, when you increase the concentration of stuff, the rate will go up. This also applies to gases and pressure. So if you have a reaction that is occurring in a balloon or something, and you put more gas in there, the pressure goes up. And so if pressure increases, the faster the reaction will go. This is why if you give somebody oxygen in like a tank, like you have to control what the rate of oxygen is that goes into them. If you put too much oxygen, then the oxygen will dissolve into their blood too quickly, and then you do that reaction too fast, and that's bad. If you don't put enough oxygen, or maybe like because somebody has breathing problems or they need assisted ventilation or something like that, then not enough oxygen means the reaction goes too slow. The next thing we're going to talk about is temperature. Remember that temperature is how fast molecules move if they're in the gas phase as well as in the liquid phase. Therefore, if molecules move faster, they have more energy. And if molecules have more energy, they can get over the activation energy. And so as a result, if I have a sample of stuff and the amount of energy I need is to get over is this much, but the molecules have on average this much energy, they won't get over the hump. But if on average they have this much energy, then some of the molecules do get over the hump. And so the reaction will go on its own. So by heating stuff up, you can create a situation where the molecules will react more often. And so we have a demo right here for that too. And this is going to be glow sticks in water, which is not super easy to see on the screen, but we'll do the best that we can. All right, so we'll open this guy up. There we go. There's our glow sticks. They should have the same brightness, although it's kind of, it looks like to me that the one on the right is a little bit less bright. But looking at the middle, they should have the same intensity. We're going to put one in hot water and we're going to put one in cold water. Which one's which? Tell me in the chat after we speed up the video. So here's the first one. And here's the second one. And then we're going to speed... I'm going to actually speed up the video by going like this. So I'm going to advance a few seconds every time. All right, so that's the end state. Let's look at it at the start again. Boop, 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 boop. Oops. There we go. All right, so which one was hot and which one was cold water? Left or right? Which one was which? The hot has to be on the left. How come? What made you draw that conclusion? So if the reaction is the glow sticks emitting light, and we put it in the hot water, and it shines more light, the reaction must have gone more, right? So the hot water provided enough energy to make the glowing reaction occur. Whereas the cold water suppressed that. It made the molecules slow down so that the reaction did not occur as often. And the result is you get less light. And so he's going to take these out of the container now. And once the focus dies down, you could see the difference. If you've ever had glow sticks, something that people say is, oh, I want to keep them forever. Okay, throw them in the freezer. Because what that means is that the reaction will go less often. And then when it warms up, it'll get bright again. So this is why you freeze your glow sticks. I'm not saying this as a professional raver. I'm just saying this as somebody who's a scientist and also likes studying that stuff. So, all right. We got to make glow sticks in a chemistry class, which was great. Then we turned off all the lights in the lab, and then we shook the vials that we had them in. Nobody told us that that stuff is carcinogenic and that you really shouldn't be exposed to it. So we were a bunch of goofy second-year students running around a lab with the lights out. Probably not the best idea, but our TA was cool about it. All right, here's the last video. This is with regards to a catalyst. A catalyst is a special substance, and what it does is it changes the reaction diagram. In doing so, it is not used up and can be used over and over again. So what the catalyst does is you put it in there, and it just allows the reaction to go indefinitely in a different way. So what that means is that if this is the normal reaction that I might have, I might need this much energy represented by the red line. If I add a catalyst, that curve will change. Now I only need this much energy because the catalyst has provided a different path for the reaction to go. For instance, A might react with B to make AB here, but in this reaction, A might react with the catalyst, and then the catalyst A reacts with B to make AB, and the catalyst is left over. Or it could be any number of things. This little divot represents some sort of intermediate product that the catalyst is involved in. So if you see these little, like, valleys in your energy diagram, that's because a catalyst is in there. All right, now, the amount of energy that we need for the catalyzed reaction is lower, which means that the reaction must go more quickly. Because remember, if I have my average energy of my molecules is like this much, then only the ones that have enough energy get over. But if I have the same energy available on this side, then all of these molecules can react, and the reaction's going to go way faster. So let's see that in action here. This is a reaction that I would have done today, believe it or not. At the science fair for Everett Community College, which we usually do every year in the second to last week of classes for spring, we invite a bunch of 5th graders from nearby high schools, and we do this reaction. And I actually do this specific reaction. I put peroxide in a giant flask, as you're about to see a scientist do. This is actually where I got the idea. And you put in a potassium iodide catalyst, and it causes the reaction to go very fast. Now, this reaction is kind of slow because it's peroxide. That's not the color I wanted. Sorry about that. So this is peroxide. If you have peroxide under your sink or in your medicine cabinet or whatever, it's stored in a black bottle or a brown bottle. And the reason for that is that we need to store it in some sort of plastic container with a color so that light doesn't pass through it. We can't use transparent plastic. The light needs to be absorbed. Generally, darker colors absorb light more, so we use that specific color for that bottling. If it is exposed to light, it will decompose. And so it will decompose on its own, but it's very, very slow. But if we add a catalyst to it, such as, in this case, sodium iodide. I use potassium iodide because it was whatever's in the stockroom. The reaction goes way more quickly. The peroxide binds to the iodide, and that allows it to remove an oxygen to make O2. And so This reaction is known as elephant toothpaste. This is probably one of my favorite things to do for science. And fortunately, we have somebody who has done that for us already. And his name is Science Bob, and here he is on Jimmy Kimmel. So hopefully the stream will not immediately go down because I'm playing Jimmy Kimmel for you guys. Science Bob may claim this, whatever, but here we go. We'll see what happens.
We're going to start with a little bit of actually dish soap. So if you want to put some dish soap in your flask.
How much? Just a squirt?
Yeah, a little more. That's good.
Okay.
So dish soap will keep the bubbles because we're going to remove the oxygen. They'll hold the oxygen.
Okay.
So I'll put a little bit in here. All right. Next, coloring.
So something I do want to comment before we continue. Every time a liquid is added to the container, music plays, and I kind of wish that this was a real thing. Like, I'm just go to the fridge and pour some soda in, and then I get happy music playing.
We have green and red. Do you have a preference?
I'll take red.
All right.
Specifically this music.
Christmassy. How much is this?
And just keep going. Keep adding a lot of
Okay.
that. That's good. A little more.
This is going to be delicious.
All right.
Is this how you did your jacket?
That's good there.
Okay.
All right, so I'm going to add the hydrogen peroxide because you don't want to do that.
Okay. Oh, it's dangerous,
This
right?
is
Okay.
And actually, yeah, let's get all geared up here.
Okay.
Now remember, safety first in the laboratory.
There we go.
Not that we've had a
All
laboratory.
right, so in goes that. And
Now, what's happening here? What process are we about to see?
So here's what we're going to see. We're going to, in order to remove the oxygen, we're going to use a catalyst.
Okay.
Catalyst will speed up the reaction. So we're going to, that's what's in here. It's a sodium solution. We're going to pour that in, and that's going to remove the oxygen. The soap is going to hold it,
And we're going
and
to smother to death, all of us.
we'll be okay, but it will create a lot of bubbles really fast.
Okay, great.
And usually this is done in graduated cylinders, but we're going to make it a little more intense with these ridiculously large flasks.
Okay, good.
All right, so this is what you're going to use. We're going to pour that in there. The oxygen will be released, and we'll watch the reaction. We're going to
Okay.
need to step back after we pour it.
Okay.
All right.
All right, so before we start the reaction is currently going, and if you left this here, all the peroxide that's in there would decompose. The dish soap is added to catch the oxygen that comes out, so as the reaction occurs, bubbles will appear. You can barely see the bubbles down here, but that's probably just from mixing. It would take years for all the peroxide to decompose completely. But when we add the catalyst, this happens.
Here we
Step
go.
back.
Ready? In 3, 2, 1, pour. There we go.
Whoa! Whoa! Wow, that's great. That's like Ghostbusters. Wow. Whoa! That's something.
And they'll never get that light clean, unfortunately. But, yeah. So, that is the elephant toothpaste reaction. I do that for kids. Thanks, Science Bob, for giving me the idea. The fifth graders love it. We get thank you cards from them, and they always say the best thing was the elephant toothpaste. And then of course there's always the people that are like, oh, I thought it was going to be bigger. Why isn't it bigger? I'm like, well, you get what you get. All right. Hopefully my channel will still be up next week. You know, the quarter's over, so that's all right. But please don't copyright strike me, Science Bob. All right. So for our review question, let's summarize really quickly here. So what are the things that govern how fast reactions go? So we care about the physical nature. If we can get a higher surface area, we can speed up the reaction. If you just put more stuff in, the reaction will go faster. If you heat it up, it'll go faster. And if you put a catalyst in, it'll go faster. So with that in mind, I'm going to put this on the screen here. I'm going to give you a few minutes to answer these questions. Question number 1 is, why do you store milk in a sealed container in the fridge? Why don't we just put it in a bowl on the counter? Why do we specifically do this action? Put it in a bottle and put it in the fridge. Give some reasons on why we do that using kinetics. And then secondly, I have a reaction that turns a solution dark blue. I guess this isn't me because this is a woman doing this reaction. She notices that the chemical in her reaction only goes for 10 minutes. She wants it to go longer. What could she do if she wanted to make the reaction go for longer? And then what else could she do if she wanted to make it speed up and go faster? Okay. So answer these questions. We'll go over the answers in just a bit, and then we'll take a break. So I'll see you in a bit. All right, so hopefully we've given this a little bit of thought and we have some idea here. So let me do that. So let's look at this first question real quick. So the question is, why do we store milk in the refrigerator in sealed containers? So here's my milk jug. And it's got a little handle on it or something like that. There we go. And so when you buy the milk, it's usually filled pretty good. And here's the lid that you put on it. So there you go. So there's our milk. Now, when you store it in the fridge, The fridge is generally cold, so what does having it cold do to the speed of the reaction? Well, if it's cold, we slow the reactivity of the milk down. And what I mean by reactivity of milk is like things like bacteria or curdling or any specific process that we would not want to happen to the milk. The other thing that we're doing is when we have it in a bottle like this, we're reducing the contact area that the milk has with the surroundings. And so the only place that the milk can really contact the atmosphere or anything outside of the bottle is right here at the surface. So by putting it in a bottle, the bottle reduces the surface area, which in turn slows down any reaction that might be going on. Now, you could also give other reasons, like, oh, we put it in the fridge, and inside the fridge there's no light, so light can't catalyze any bad reactions or cause any bad reactions to occur. We use plastic containers because they're inert with the milk. We wouldn't want to store it in, say, like, a container that had a catalyst that would accelerate how it spoils. Things like that. Those are the answers that I'm looking for with this question. All right, for the second question, if I have a reaction that is 10 minutes long and I want it to last longer, do I need to speed it up or slow it down? Now, if I speed it up, it will last less time, so I need to slow it down. So what are some things that we could do to speed up the reaction for the second part of the question, or slow it down for the first question? And so those answers should be on the previous slide, which is right here. And so we can just look at these. If I want the reaction to go slower, I need to do the opposite of all of these things. I guess I could just go to this screen here. So I would need to not use a reactant that is ground up finely. I would not need to dilute the reaction, maybe by adding water to it. I would need to cool the reaction down. And then I would not want to use a catalyst. Those four things would make the reaction go slower. If I want to do it faster, I would do the opposite, which is all the things that are highlighted on the previous page. I would grind up the reactants, make them really fine. I would concentrate them by removing water. I could heat up the reaction. I could add a catalyst. Okay, that's catalysis, and that's all that we're going to do for that section. So there's the homework practice at the bottom. I'll leave that on the screen for just a few more seconds so you can write that down if you want it. And then I am going to put the title card up, where we will put the timer up, which is hiding because it's down here. Here it is. Oops. I need to reset that. Hold on. Reset timer. Boop. Oh, and we got to put break time so everybody knows. All right, start the clock. Start the music. And I'll see you in a bit. That's close enough. Oops. I clicked the wrong thing. Alright, so... Let's see, where are we now? Oh, we're on equilibrium. Okay, so let's turn these off. Click here. And let's talk about equilibrium. Equilibrium's kind of a weird concept that a lot of first-year students struggle to understand. And what it is the tendency for a reaction to reach a point where it makes so many products that the products then react and turn back into reactants, and you eventually just don't have any more change in the amount that you have. The reactions keep going, but the amount that is there remains constant. And in order to do that, I actually need to set up something really quickly here. So let me see here. That's not what I want. That's the one I want. Okay. No, it's not the one I want. Sorry, hold on. There we go. Oh, it wants me to download it. I already have it downloaded. Okay, sorry. We have... Oh, I ruined the chat. Hold on. I'm trying to move the chat out of the way so I can get to my computer. Where the heck is this? That's shapes. I don't want shapes. Well, I'll just download it again, whatever. PHET, stop. Wait, open. Oh, shit, hold on. Isn't this Java? Oh my goodness, I hate everything. Normally I just double click on this thing to make it work, and I apologize that this isn't working. Give me a second. Let me just put this back on for a sec. And I'll let you know when I have it working again. So, be right back. Okay, so I didn't get it working, unfortunately, because my computer doesn't like Java. I mean, that could be my doing. I might have disabled Java. But what I can do is... So I want this window. So we were talking about equilibrium. And I wanted to describe equilibrium as a sort of process that eventually will go in both directions. And so this is what... Oops, that's not the right thing. Maybe I need to window capture? Is it... No, it's not that one. Wow, I'm just getting all the technical difficulties today. That's the chat window. Let me hit cancel. Window capture 2. There, that's the one I want. Okay. Oops, which is too small. There we go. Okay. So this is what I was trying to load. This is a YouTube video that I have paused here. So you can see on the left side where it says A, I have a bunch of green spheres. And on the right side where it says B, I have nothing. Drawn over that is what looks like an energy diagram. And this up here is the activation energy. Now if I hit play, all these balls are going to start bouncing around. Oh, I guess apparently he made more on the other side. Oh, great. He's going to talk over this. This is the problem with me not previewing my videos. But no matter what setup I have here, what will eventually happen is if you give it enough time, the balls will bounce back and forth at the same speed. And I'm trying to find a place where he actually shows that. Oh, I got to hit play. There we go. So if you had a setup like this, and you left it running for 20 minutes, and you came back, you would notice that there's going to be the same number on both sides. Because they're eventually going to bounce over, but they're going to bounce back and forth at the same rate. But if you were to change the elevation of these, like say like this, and then do the experiment, like so, they would still bounce back and forth, but you'd end up with more of them on the right. And at some point, the amount that would be on both sides would be different, but they would remain roughly constant because they're going back and forth at the same speed. There's just too many on the right that aren't able to get up over the hill, and then the few that are over here do go up. I don't know what this number sheet is going up. This video isn't super useful to me, I've decided. I will try and figure out why that demo isn't working on my computer, and we'll run it tomorrow during the lab. But now I've confused you all and wasted most of your time. Let's talk about equilibrium. Apologies that that didn't work out. I was not expecting it to crash when I booted it up. Alright, so if I give you a reaction like this, this would be a reaction that we've studied all quarter. We have reactants and products, and here's some phases and whatever. For this specific reaction, if I were to analyze the mixture at the end of the reaction, and I went looking for HCl, and I went looking for H3O+, and I went looking for Cl-, I would find that there is all of the HCl that I put in there reacted completely. And that's what you would expect for the reactions we've been talking about. You put stuff in, it reacts, and then the reactants are gone. But it turns out that that is actually the exception and not the rule for many reactions. Most reactions do something like this. So on the left we have acetic acid and water. And you'll notice that instead of having the arrow pointing to the right, it points in both directions now. The reason being, if I were to look at this reaction very closely and look for acetic acid, which is right here, or acetate and H3O+, I would find that most of it actually is still the acetic acid. Most of my stuff for this reaction is this form right here. Very little of it actually reacted, but it still reacts, so we need to put this forward arrow. It's just that in this case, if these two things bump into each other, the H3O and the acetate, they can react too, and they have a tendency to recombine. This is different from the previous reaction on this slide right here, where if these two bump into each other, they just go, huh? And bonk off, and they don't care. So no reverse reaction occurs. This doesn't happen. So it all has to do with the tendency of the reactants and the products to want to recombine and go back to what they started as. And this also is affected by an energy diagram. So suppose that I had an energy diagram where I had a really tiny activation energy and then my energy dropped by a lot. Going in this direction is easy, but going in the reverse direction is really hard. So this would be a reaction where like I have HCl over here and then I make H3O plus and Cl minus. Where going in the reverse reaction is just too difficult. But the reaction shown above could be something like this, where the energies are actually relatively close to each other, and there's not that much of a difference. It's easy to go in this direction, but it's also easy to go back. And if it's easy to go backwards, then I'm going to start creating reactants again. And the reaction's going to go back and forth. This is the premise behind how equilibrium works. Equilibrium can occur if the reverse reaction is possible. Then you just have both reactions occurring at once, and you end up finding an end point where the reaction settles to somewhere in the reaction. Here it settles at only 0.5% of it reacts. So we're going to call any reaction that can go in both directions reversible. A reversible reaction means that I can go in the normal direction that we've been writing all along, or I could take the reactants and the products and have them switch places. So I could take this guy and reverse them to get this reaction. If both of these reactions occur, then what I can do is write them both at the same time using a double arrow. So the double arrow is important because it tells us, hey, the reaction goes in both directions. Reactants can turn into products, but it's also possible that the products can turn into reactants. And whenever that double arrow is there, you should think, oh, I have an equilibrium situation. I can make the reaction go in both directions. Now, to be more specific about the definition of equilibrium, not only do you have to have both the forward and reverse reactions occurring at the same time, but you also have to have them happening at the same speed. Now, I'm going to show you some graphs in an attempt to explain that, but if I had tons and tons of reactants, I would make products very quickly. But if I didn't have any products at the start, I would not be able to produce products at all. I'm trying to think of an analogy of this. And my analogy would be something like, if you are at a restaurant that is just opened and people are preparing food, at that instant, nobody is eating. And so you are creating products, which are finished food dishes, I guess you would say. But once the food starts coming out and people start eating it, those products they're not really turned back into reactants because you're not sending it back to the kitchen. But the products are getting used up. And so as the day goes on, all of the food that you're making is being eaten up at the same speed. But at the very start of the day, you're making food faster than it's being eaten because there just isn't any food out there yet. To put that in a graph, that would look something like, let me just skip ahead here real quick. That would look like this. So for this specific reaction that I've got on the screen here, I've got the white molecules and the purple molecules reacting to make a combo. At the start, I have lots of reactants, but I have 0 products, so the reverse reaction cannot happen. But as I go on and I start to make this stuff, then I can start to turn it back into the reactants. So if HI can return back into H2 and I2, I won't be using it up at this... Oops, darn it. I won't be using it up at a constant speed. So that's what this line is relatively flat at the start means. If I were just using up the H2 and the I2, this is what would happen. I would use them up at a constant speed. Eventually, I would just run out of them, and the reaction would stop. And then I would just make this stuff at a constant speed. And that would be as much as I could make because I ran out of stuff. But as you can see, the reverse reaction does not allow this to happen. I don't just run out of I2 and H2. Instead, the amount that I have kind of curves to this flat plateau. At the start here, I'm using up I2 quickly. But over here, I am using it up less quickly relative to the amount that I'm making it back. And once I cross this dotted line right here, I'm making it at the same speed that I use it. Once the reaction reaches the point where both the products are made at the same speed that they're used up to turn back into reactants, we get this. This is called dynamic equilibrium. Equilibrium needs you to have both reactions occurring at the same time, so we have a double arrow. But I have to make my reactants just as fast as I'm making products. If I wasn't making them at the same speed, this wouldn't be flat. I would have either less or more of it, depending on what was happening. But if I'm making them at the same speed, the amount that I have is relatively constant. And so all of the concentrations become constant at equilibrium. The reaction is still going, we're just not making any more. If I make 2 pies every hour, and my customers eat 2 pies every hour, and I start with 5 pies out on display, I could bring out 2 pies to replace 2 that are eaten, but the number that will be out there will always be the same number. They won't be the same pies, but the amount that is on display for people to look at and then purchase will always be the same, because I'm making them at the same speed that they're being eaten. With molecules, it's the same thing. If I make HI at a constant speed that I break it apart into these two things, so let's say for every one of these that forms, this one will then split apart, the amount that I have is equal. And so this is equilibrium. So let me go back to this previous slide that I skipped over. And those are our 2 qualifiers. We need both of those 2 things to occur. So both reactions have to occur forward and backwards. And I also need the speed of the forward reaction to equal the speed of the reverse reaction. If one is too fast, I will accumulate stuff and use up the other one. They have to be the exact same speed. Let's look at this visually. I don't know why this one isn't animated. Let me see if I can fix that real quick. Oops. Oh, I see why. Okay, so if I do this... So stuff is going to appear really quickly, so hold on. And I want this to... Okay, sorry, just a second. Okay, that should work. We'll see if it works. All right, here's our reaction. At the start, I haven't allowed the reaction to start yet, because I haven't started the timer. But initially in the container, all we have are H2, which is the white one, and I2, which is the purple one. As I let the reaction progress, some of the reactants form. And I'm going to highlight those with this, just so you can see how many there are in there. So after about 15 seconds, I have 4 products that have made. After a little bit more time goes by, I will still keep making these, but for every one of these that I produce, I increase the likelihood that they will bonk into each other and then fall back apart into H2 and I2. And at some point, there we go. I'm going to have the same amount in the container regardless of how much time passes. So over in diagram C, I highlighted 8 of them. And in diagram D, I've highlighted 8 of them as well. So because my amount is staying constant, somewhere in here, I reached dynamic equilibrium. So equilibrium happened around 30 seconds or so. And again, well, so here's the demo that I was trying to run. So here's the link for it. If you want to try this, it requires Java, and apparently I don't have Java enabled on my computer because I've banned it, because it's a security issue. But if you don't have that issue, you could try looking at this link. It will ask you to download a file, and then you could play with the equilibrium simulator. And then you can see what we're trying to do here. I'll see if I can do something about that tonight, but if I can't, then I'll just have to leave it. Alright, so let's go to the next. That's just our summary. So this is everything we just said. So equilibrium happens with all sorts of situations. Many reactions are at equilibrium. And depending on the nature of the reaction, you may or may not want that to happen. For example, if I am working in industry and I do a reaction to produce, say, ammonia. Ammonia is important because we use it for fertilizer. But the reaction reaches equilibrium very quickly and I don't have many products. I might not want the reaction to reach equilibrium because that means I'm stopping the production of things that I want. So I would have to manipulate it. Other reactions, we do want to go to equilibrium because we don't want the reaction to be occurring anymore. For example, if we use vinegar, vinegar is acetic acid. And if it's not at equilibrium, it would not be as acidic and it would not provide as much flavor. So putting acetic acid into water, it will quickly reach equilibrium, makes it have the distinguishing taste that it has. Other more serious consequences would be things like your bodily functions. If your body reaches equilibrium, then reactions stop producing products, such as like heat. Like if your body stopped producing heat, that'd be because you died. So you don't want your body to reach equilibrium. That would be bad. So we keep providing it food so that the reaction that produces energy keeps getting driven in the forward direction. So equilibrium is not inherently bad. It is a thing that exists. And it's important for us to understand more or less what the conditions are to create that. Now, equilibrium will eventually settle to some ratio. Like before I told you that 99.5% of acetic acid will stay whole in a container that has it in water. And 0.5% of it will dissociate. We're going to relate the amounts of reactants and products that equilibrium settles on by giving it a number. And so the number is called the equilibrium constant, K. And I'm going to put a scary formula on the board here. If this is my reaction, I have A and B reacting together to make C and D. And C and D could react with each other to make A and B again. This is the value of K. And you're probably looking at that and going, oh my god, I don't want to do any more math this quarter. I'm so sick of it. And that's totally fine, because we're not going to calculate this. What we're going to instead do is interpret what it means. Here I have my products. That's C and D. On the bottom here, I have my reactants. That's A and B. So what I'm instead going to write this expression as is this. Products divided by reactants. And that's going to be close enough for approximation for K. Now, let's suppose that I had a mixture that was 50-50 products and reactants. There's the same amount of products as there are reactants. And then you put in numbers for how much products and reactants you had. So if I did, I have 50 of these and 50 of these, what would K be equal to? 50 divided by 50 is just 1, right? So if I enter numbers for these things, and the numbers I enter are the same, K is going to be 1 because I have exactly the same amount of products and reactants. What would happen if I had more products than reactants? What would be the value of K? Would it be bigger or smaller than 1? You can type that in the chat with your guess. It doesn't even really have to be a guess, because I'm sure that everybody knows how mathematics works here. So if I had more products than reactants, so like say 90 products and 10 reactants, would K be bigger or smaller than 1? There you go, it'd be bigger. Yeah, because a bigger number on the top and a smaller number on the bottom means a bigger number. So if K is a large number, I must have mostly products. What if K was a smaller number? Well, I must have mostly reactants. So these next few slides are going to show this as like a seesaw. Now, unfortunately, my y-axis has to be upside down to make these numbers work. And so, in order for this to work, so numbers at the top here, where's my cursor? There it is. Numbers at the top will be very small. Numbers at the bottom will be very big. If I have a 50-50 mixture where everything is equal, the middle value will be 1. So if I have equal amounts of reactants and products, the equilibrium value, or the value of the equilibrium constant is just 1, like we said before. If I have all products and no reactants, that would be like dividing a number by 0, which is not actually a number, but if you picked a really big number and then a really tiny number for the reactants, you get a number that was essentially infinitely large. So bigger numbers represent more products versus reactants, all the way up to infinity, where infinity would be the value of all products and 0 reactants would be the equilibrium constant for that. If I did the other direction, and I had no products and only reactants, I would have 0 divided by some number, and that's just 0. So if I have only reactants, my equilibrium constant is 0. So what that means is that if we look at our ranges here, any number between... Oops, I thought that was the pen. Any number between these would represent mostly reactants. So if K is between... Well, it can't be equal to 0, I guess. Well, I guess it could be. If K is between 0 and 1, we have mostly reactants, because that's how the math works out. This is just going to bug me, so I'm going to get rid of that. And then if my K value is larger than 1, I have mostly products. And that would be anywhere in this region down here. Now, if K is equal to 1, then that's when we have the 50-50 mixture. Okay? So your job is going to be to look at a K value and tell me about the reaction. Okay? So for instance, let's suppose that I had this reaction again, and I told you K is equal to 1.8 times 10 to the minus 5. That's this right here. Is that a big K, a small k, or a 1K? What do you think? 1.8 times 10 to the minus 5. Is that bigger or smaller than 1? What does 10 to the minus 5 mean? What does it mean when we have a negative exponent? It means a small k. Yeah, I knew what you meant. There you go. Yeah, so if you have a number with a negative exponent, remember that is a decimal. That's a really tiny number. So this number is very small, which means that I have mostly reactants. And if you remember before, when I said that I have 99.5% acetic acid in here and the other amount of products is 0.5, I actually calculated that using that equilibrium expression. And you can do that, but I'm not going to make you do that in this class because that's too much math. I make third quarter chemistry students do this, and they have a tough time, so I'm not going to make you guys do it. All right. And there's our summary again. So K is between 0 and 1, mostly reactants. K is bigger than 1, they're mostly products. If K is close to 1, there's about the same products and reactants. Now, what do I mean by close? I mean, like, if it's a one-digit number, that's good enough. Or if it's, like, within 0.1, that's fine. So on this slide, I have some examples for you, and I want you to tell me, where do the amounts of stuff lie in each of these reactions? So here's a K for reaction 1. Are there mostly reactants or products? Here's reaction 2, mostly reactants or products. Reaction 3. So I'm going to give you a few minutes to do that because the class is about to end. So highlight the side of the reaction where most of the stuff lies. We'll go over the answer in just a second. All right, let's go over the answers here. So like we said before, if K is big, and this is a number larger than 1, we're going to have mostly products. I'm saying the wrong thing, but I'm highlighting the right thing. This K is pretty close to 1, so you could just say it's in the middle. But you could also say, oh, maybe it's more towards reactants. So either of those is okay. I was intending for you to say it was about 50-50. This K is very small, so there is definitely more reactants. All right. So that's how we describe the equilibrium constant in terms of a number. And how we describe equilibrium in terms of, oh, both reactions can happen, and we're going to eventually settle to some midpoint. I'm sorry I couldn't get that demo to work. Again, I'll look into it. We'll see what I can do. But that is all that we have time for today. So I want to thank everybody for coming out to lecture tonight. Thanks for watching. If you have any questions, make sure to get them to me so we can talk about them tomorrow. Tomorrow's lab lecture. Oops, we're off the break here. Tomorrow's lab lecture, I will talk to you a little bit about the solubility experiment, which is mostly just, hey, watch all these videos and see how things dissolve in each other. Shouldn't be too much of an issue. Then we're going to talk more about this stuff, and we'll continue our lecture. Probably start Chapter 10 tomorrow. So make sure that you are able to come out for that or watch this on the YouTube blog when you can. Have a great night. Make sure that you're prepping for exam number 2. And stay safe, stay healthy, stay home.